Piping networks in pump selection. Piping systems typically involve several types connected to each other in series or in parallel, as shown in the figure. When the pipes are connected in series, the flow rate through the entire system remains constant regardless of the diameters of the individual pipes in the system. This is a natural consequence of the conservation of mass principle for steady incompressible flow. The total head loss in this case is equal to the sum of head losses in individual pipes in the system, including the minor losses. The expansion or contraction losses at connections are considered to belong to the smaller diameter pipe since the expansion and contraction loss coefficients are defined on the basis of the average velocity in the smaller diameter pipe. For the pipe that branches out into two or more, or what we call parallel pipes, the head loss is the same in each pipe, and the total flow rate is the sum of flow rates in the individual pipes. Therefore, the relative flow rates in parallel pipes are established from the requirement that the head loss in each pipe be the same. This result can be extended to any number of pipes connected in parallel. The result is also valid for pipes for which the minor losses are significant if the equivalent lengths for components that contribute to minor losses are added to the pipe length. On the other hand, the analysis of piping networks, no matter how complex they are, is based on the two simple principles. The first one is that conservation of mass throughout the system must be satisfied. This is done by requiring the total flow into a junction to be equal to the total flow out of the junction for all junctions in the system. Also, the flow rate must remain constant in pipes connected in series regardless of the changes in diameters. The second is pressure drop, and thus head loss between two junctions must be the same for all paths between the two junctions. This is because pressure is a point function and it cannot have two values at a specific point. In practice, this rule is used by requiring that the algebraic sum of the head losses in a loop be equal to 0. A head loss is taken to positive for flow in the clockwise direction and negative for flow in counterclockwise direction.
Most piping systems encountered in practice, such as the water distribution system in cities, commercial, or residential establishments, involve numerous parallel and series connections, as well as several sources and loads. In many pipe systems, there is more than one pipe involved. The governing mechanisms for the flow in multiple pipe systems are the same for single pipe system discussed. The simplest multiple pipe systems can be classified into series or parallel flows. When pipes are connected in series, the flow rate through the entire system remains constant, regardless of the diameters of the individual pipes in the system. The total head loss is equal to the sum of the head losses in individual pipes in the system, including minor losses. In general, the friction factors will be different for each pipe because of Reynolds numbers, which is REI is equals to PVIDI over U, and the relative toughness, which is EI over DI. For a pipe that branches out into two or more parallel pipes and then rejoins at a junction downstream, the total flow rate is the sum of the flow rates in the individual pipes. The pressure drop in each individual pipe connected in parallel must be the same, since delta P is equals to PA minus PB. And the junction pressures PA and PP are the same for all individual pipes.
In the analysis of piping systems, pressure losses are commonly expressed in terms of the equivalent fluid column height called the head loss. The head loss represents the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in the pipe. The head loss is caused by viscosity and it is directly related to the wall shear stress. There are many ways to compute for head loss. First is the Darcy-Weisbach formula. Using the Darcy-Weisbach equation requires you to know or calculate the Darcy friction factor, or F, which is a function of the fluid properties and a pipe material. In English system, this is the Darcy-Weisbach formula. where G is 32.2 FPS squared. And if the problem has a discharge and in unit cubic feet per second, you can use this formula. For the SI unit system of Darcy-Weisbach formula, you can use this, where the gravity is 9.81 meter per second squared. And if the problem has involved a discharge in cubic meter per second, you can use this formula. The Manning equation can also be used to compute head losses in a pipe flowing full. The procedure for this is really no different than the process described in computing the flow profile in an open channel. The English system of Manning's formula that involves velocity and feet per second is this. And the other one that involves discharge in cubic feet per second is this. So in the SI version of Manning's formula, again that involves velocity in unit meter per second, is this formula. So for the other formula that involves discharge in cubic meter per second is this. Now for the Hazen-Williams equation, the difference between Darcy-Weisbach and this equation is that the Darcy-Weisbach has a friction factor, which if you're not given anything to help you calculate F, then there's a good chance you should be using the Hazen-Williams equation, which requires you to know the Hazen-Williams coefficient that just depends only on the pipe material. The English system units of Hazen-Williams formula is this, where you can use this formula to derive missing quantities, like discharge in cubic feet per second, and the Hazen's coefficient that depends on the material being used. And this is the SI version of Hazen-Williams formula. And then which these following formulas can be used to derive missing quantities.
Venturimeters are flow measurement instruments which uses a converging section of pipe to give an increase in the flow velocity and a corresponding pressure drop from which the flow rate can be deduced. So a venturimeter is a device which is connected in between the pipeline. As you can see in this illustration, it has three parts: the converging cone, the throat, and the diverging cone. Also, we have here two sections in the illustration where the fluid travels from the area of section 1 to the area of section 2. Considering that this whole system is a closed system, based from the conservation of energy principle, the total energy at section 1 must be equal to the total energy at section 2. In addition, the mass in a closed system is also conserved, so the volumetric flow rate at the area of section 1 must be equal to the volumetric flow rate at the area of section 2, and this can be expressed by the continuity equation. Now, when the fluid enters the throat of the venturi, since it is smaller than the area of section 1, the fluid must travel faster in order to maintain the same volumetric flow rate with the area of section 1, and this increase in velocity at the area of section 2 decreases the pressure in the area, which follows the Bernoulli's equation. After passing through the throttling, the fluid travels to the diverging cone, which restores the pressure as nearly to the actual value. So Venturi measures a fluid's flow rate by reducing the cross-sectional flow area in the flow path and generating a pressure difference. This pressure differential follows the Bernoulli's equation, which can be expressed as the pipeline is horizontal, based from the illustration, Z sub 1 is equal to Z sub 2. So we can cancel them out from the Bernoulli's equation, and by doing that, we can arrive at this expression. Now, by rearranging this expression, we can get the pressure head difference. Going back to the continuity equation, we can solve for V sub 1, and by substituting this to equation 1, we can solve for V sub 2. By substituting V sub 2 to the continuity equation, we can get the theoretical discharge, and the actual discharge can be evaluated by multiplying the coefficient of discharge with the theoretical discharge.
Orifice. Orifice is any opening having a closed perimeter made in wall or partition used for measuring flow of fluids. Note that when the area of the tank is more than 16 times the area of the orifice, neglect the velocity of the water in the tank. The differential flow meters is the most common device for measuring fluid flow through pipes. Flow rates and pressure differential of fluids such as gas, vapors, and liquids are explored using orifice plate flow meter. The differential flow meters, whether venturi tube, flow nozzle, or orifice plate style, is an instrument that is installed between two pipes flanges. The orifice plate of the flow meter is comprised of a circular metal disc with a specific hole diameter that reduces the fluid flow in the pipe. Pressure taps are added on each side of the orifice plate to measure the pressure differential. According to the laws of conservation of energy, the fluid entering the pipe must equal to the mass leaving the pipe during the same period of time. The velocity of the fluid leaving the orifice is greater than the velocity of the fluid entering the orifice. So when applying Bernoulli's principle, the increased fluid velocity result in a decrease in pressure as the fluid flow rate increases through the pipe. Back pressure on the incoming side due to the restriction of the flow created by the orifice plate. So the pressure of the fluid at the downstream side of the orifice plate is less than the incoming side due to the accelerated flow with a known differential pressure and velocity of the fluid. The volumetric flow rate can be determined.
Orifice unsteady flow. Unsteady flow is a flow velocity and area flow of various type. In unsteady flow, we have two conditions here. The height increases or decreases. Either way, it is unsteady because it varies with respect to time. We have an example here. Suppose we have Q in here and we have Q in here and we have Q out here and we have Q out here. So in the two vessels we have Q entering and then we have Q out or Q leaving. So assuming that the height of the liquid is increasing, so when will this happen? So the height of the liquid will rise if and only if Q in is greater than Q out. Otherwise, the height of the liquid will fall if Q in is less than Q out. So, if that happens, we have the height as a falling head. If we talk about steady flow, the head or height is constant, and if it is unsteady, it is changing with respect to time. Here, we have a time to discharge a liquid on a vessel through an orifice. So, this is our illustration. This is our AS, which is the cross-sectional area of liquid surface or vessel. This is our H1 or our height 1 or the initial head producing the flow. This is our H2, which is the final head in producing the flow. And this is our AO, which is the area of the orifice. Here, we have an equation to get some of the unknown in the given. So, if it is general shaped vessel with an orifice at the bottom, we will use this equation. And for variable cross-sectional or the area for the cross-sectional, we will use this equation. For constant AS, if the AS is constant, we will use this equation. And for the submerged orifice, we will use this equation.
Pitot tube is a flow measurement device used to measure fluid flow velocity. It is widely used to determine the airspeed of an aircraft, water speed of a boat, and to measure liquid, air, and gas flow velocity in certain industrial applications. When the fluid enters the pitot tube, the velocity of the fluid particles becomes zero and it is converted into dynamic pressure. So we get the stagnation pressure, which is the sum of the static and dynamic pressure. So, stagnation pressure represents the pressure into the point where the fluid velocity has come to a complete stop. Now, let's see this Bernoulli equation and derive this formula for the velocity of the fluid. Let's take 2 points, point 1 and point 2. Point 1, the velocity of the flowing fluid is v, and the point 2, velocity inside the pitot tube is 0 as the flow has become stagnant here. Now, since both of the points are at the same elevation, so z1 and z2 gets cancelled and the v2 is equal to 0. So the equation here is cancelled. Now, if we rearrange the equation, we get this form. So here, P2 is the stagnation pressure while P1 is the static pressure, and V1 squared over 2 times rho is the dynamic pressure. We can see here from this equation, we can get the velocity of the fluid. And now, by using a manometer, we can calculate the velocity of the fluid. As we can observe, the pressure in the pitot tube in the side is more than the other side, so it has more height in the manometer than the other side. So using the difference in the manometer height, delta H, we can calculate the pressure difference. So from this equation, that one, we can derive again the formula and have the velocity of the fluid.
Tubes and pipes measures the flowing fluid or air velocity. That by means this is the entrance of the flowing fluid is the where it came out. So here the differential pressure. So basically a differential pressure flow meter pipette tube measures two pressure, which is the static and the total and path pressure. Static pressure is the operating pressure in the pipe, block, or the environment, upstream to the pipette tube. In solving in the pipette tube in pipes, we were using this formula. P1 times S1 over Pg plus Y S1 plus H S2 minus H plus Y times the S1 is equal to P2 S1 or Pg, where V is equals to the velocity of flow of the fluid having the specific gravity of from this S1 or the initial. And Ct is equals to the coefficient of the pipette tube, and S1 represents the specific gravity of liquid flowing in the pipe, and S2 represents the specific gravity of fluid in the manometer. And by all that means, this will be our final, or we arrived this final formula in solving the pipette tube and pipes.